Hello, ladies and gentlemen. Let's continue on with the mass balance today. So last time in the previous lecture, we applied the Reynolds transport theorem for beta equals mass, and we derived conservation of mass for an open system. So let's do an example or two today involving application of the mass balance. And let's see if we can figure out how to do these sorts of problems involving mass balance on open systems. So topics today: open systems, we're going to deal with the mass balance, see what kind of information that yields us on problems and on situations, and we'll do a couple of examples. Okay, so let's look at what we're going to do today. Let's do an example here. What we have is a duct in which air flows in on the right and out on the left. Now, this duct contains a heating element. So this heating element is dissipating electric work in the form of heat into this air duct. And so the air, as it flows in from the left, passes over the heating element and flows out on the right. Enters on the right, passes over the heating element and flows out on the left, gets heated. So if the inlet is location 1 and the outlet is location 2, the air gets heated, so T2 is greater than T1. Now, if we assume that this is a constant pressure situation, so the pressure at the inlet and the outlet is the same, then we can say that density goes down as we heat the air. As an ideal gas or a gas gets heated, density tends to go down. As a gas is cooled, density tends to go up. So we have some numbers here. The density on the right, the inlet, is 1.2 kilograms per cubic meter. And the density on the on the left, where it is heated, is 1.05 kilograms per cubic meter. So density goes down as temperature goes up and the air is heated in this duct. Now, what are we supposed to find here? The air flows in at a certain velocity. So we have an area for the duct. So the velocity on the right is VEL1, and the velocity on the left is VEL2. So I want to know what the ratio is of the outlet to the inlet velocity. As the air heats up, becomes less dense, presumably the volume flow rate goes up and the velocity goes up. Hopefully the air is coming out at a higher velocity than at the inlet because density is going down. And you'll see this in just a minute. Okay, so heated flow in a duct. T2 is greater than T1. Density falls as we go from the right to the left-hand side of the duct as it is heated. We're supposed to find the ratio of the outlet to the inlet velocity, VEL2 divided by VEL1. That's what we're supposed to find. Now, assumptions here. I'm going to assume everything is constant in time, steady flow, steady state. And I'm also going to assume that the flow areas, or the area of the duct, is constant. So A is equal to a constant. So those are my assumptions in this problem. Okay, let's apply conservation of mass. Let's get to the analysis here. Apply conservation of mass and see if that can yield us a ratio of velocities between the inlet and the outlet of the duct. So analysis. So let's write down conservation of mass. So mass conservation. By the way, let me draw my system here. The dashed line here is my control volume. So this dashed line, is the control volume, or if you like, CV. It's my control volume on my system. It's clearly an open system because we have an inlet at location 1 and an outlet at location 2 in which mass passes across the system boundary. This is not a closed system. This is an open system. So We can apply conservation of mass to this open system and see what we get. Let's see here, mass conservation. So we have the time rate of change within the control volume is equal to the sum of the mass flow in minus the sum of all the mass flow out. Okay? We may have multiple inlets, multiple outlets. That's what the summation signs are for. Now, steady state, steady flow. Nothing varies in time. Steady state means the amount of mass is not changing within the control volume. So there's a certain amount of mass inside my duct. It's not going up or it's not going down. That's what steady state refers to. No changes with respect to time. So dmCv/dt, change in mass within the control volume with respect to time, is 0. Why? Because this is steady state. So that term is 0. Now, how many inlets do we have and how many outlets do we have? Let's go back to our control volume and figure out what these summation terms are. I have one inlet at location 1 and one outlet at location 2. So I'm going to put in m.1 and m.2 for my inlet and outlets. So my inlet is at location 1, so I have m.1. I have one inlet at location 1, and I have one outlet at location 2. So this implies 0 is equal to m.1 minus m.2. That's what mass balance says. Let me take the m.2 term and put it over on the other side of the equation. What does this imply? m.2 is equal to m.1. The mass flow out is equal to the mass flow in. m.2 is equal to m.1. Outflow equal inflow. Outflow equal inflow. Pretty intuitively clear. What flows into the duct? What flows into the duct? At the inlet at location 1 must flow out at the outlet at location 2. That's all that mass balance says in steady state. Inflow has to equal outflow. Pretty simple so far. Okay, let's calculate. Let's actually write an expression here for these m dots. So m.2, the outflow, what's that equal to? Well, the outflow is equal to the density at the outlet times the velocity times the flow area. So there's some kind of flow area, okay? And we're actually assuming that this flow area is constant because the duct is assumed to be constant area. So m.2 is equal to the density at location 2 times the velocity at location 2 times the flow area at location 2, which is equal to the flow area A flow. We're assuming it's all the same. Same thing for m.1. The inlet flow, mass flow rate, that's equal to the density at the inlet times the velocity at the inlet times the flow area, which is constant throughout the duct. Let's make the substitution here into our mass balance. So we get rho 2, velocity 2, area flow equals rho 1, velocity 1, area flow. Notice the flow areas are the same, they cancel out. We're assuming that this is a constant area duct. And I get outlet density times the outlet velocity is equal to the inlet density times the inlet velocity into the duct, all right? Let's solve for the ratio VEL2 over VEL1, which is what we want. Velocity at the outlet divided by velocity at the inlet is equal to density at the inlet divided by density at the outlet. So the ratio between the inlet to the outlet velocity is equal to the inverse of the ratio of the densities. So what that says is, my inlet density is highest and the outlet density is lowest, that means my outlet velocity is going to be high and my inlet velocity is going to be lower. Okay? Let's plug in some numbers here. Let's see, inlet and outlet velocity, 1.2 and 1.05 kilograms per cubic meter. 1.2 kilograms per cubic meter, 1.05 kilograms per cubic meter. Kilograms per cubic meter cancel out, and we get a dimensionless number. Velocity out over velocity in is dimensionless, so we better get a dimensionless number. Let's see here, 1.2 divided by 1.05. 1.14 is the ratio of the outlet to the inlet velocity. VEL out over VEL1 is 1.14. Okay, so basically the outlet velocity is 14% higher than the inlet velocity. The outlet velocity is 14% higher than the inlet velocity. Okay, pretty simple problem. Steady state problem, application of the mass balance. Pretty simple problem. Let's do another problem here. Let me pause it here for a minute. We'll get another problem set up.